welcome back to another Hyperight Data Talks. Today I'm here with Panos. Panos is Director of Observability Platform Engineering at Nike. Welcome, Panos. It's my pleasure to speak with you today.
Hi, Dana. It's nice to meet you all. Looking forward to it.
Thank you to you too. Panos will also be one of our speakers at the upcoming 10th edition of the Data Innovation Summit, which will be happening in May in Stockholm. And we're really happy to have Panos speak and share more insights. And for today's discussion, Panos, I'd like to ask you to share a little bit about what do you currently do, and to share what is your professional background and what drew you to the field that you're working currently.
I don't think it was a conscious choice per se, rather than how my career progressed, that I ended up in observability engineering. At a young age, relatively, I had to pretty much be involved with production engineering, running our own startup 10 years ago at this point. So from coming from a software engineering background into that was, eye-opening. Things in production are a lot more complicated than one might anticipate going into that. And I think my career just evolved in owning production systems, first as an SRE, and lately in observability. And being given my software background, we try to tackle these problems by building platforms internally here at Nike. That's my role for the past 2 years. And our internal customers are people who own production systems. That sums it up. Yeah.
Thank you for that introduction. My next question would be regarding your presentation at the summit. One of the topics that you'll be covering is how machine learning is transforming observability platforms. What do you think is the most significant advancement in this space over the past few years?
I think it's probably the integration of intelligent anomaly detection and root cause analysis into observability workflows. This year started a few years ago with, let's say, traditional machine learning techniques, and it has the past few years evolved into leveraging generative AI as well. This shift has fundamentally changed how engineers in production interact with and rely on observability systems. So moving the needle from just a tool for monitoring to becoming a proactive partner, a co-pilot per se based experience in maintaining reliable systems. This is significant because it addresses a number of problems that are posed based on how traditionally this whole thing works, right? As in, you go from having static artifacts or static defined data structure like metrics time series into leveraging artificial intelligence to sift through all that data and tackle problems such as scale, complexity, and becoming proactive, moving the needle measurably in terms of SRE metrics like MTTA and MTTR. This is not just an incremental improvement in observability, it's a transformation of how we think and implement it.
You mentioned intelligent anomaly detection as one of the major topics in your talk. I'm curious to hear how does machine learning improve anomaly detection when compared to some traditional monitoring approaches?
Sure. Traditional approaches have rules and limitations that stem from those rules. The core rules are that they are static and thus rigid. Thresholds are usually hard-coded, cannot adapt to changing workloads or environment variables, evolving system behavior. What's normal today may not be normal tomorrow if tomorrow is Black Friday, for example. There's also high false positives and high false negatives. Again, this goes back to having static values really. Limited scalability. As systems grow in complexity, microservices, distributed architectures, managing and tuning those thresholds for every metric becomes unmanageable simply to their scale, right? And finally, lack of context. Those data structures like metrics are fundamentally values in time, and there is not a lot of context around it's a single value. Traditional systems treat these metrics in isolation, failing to account for correlations or dependencies between the metrics. For example, how increased API latency might correlate to higher database load. Machine learning fundamentally transforms anomaly detection by making it dynamic, multi-dimensional, and context-aware. Unlike these traditional approaches that rely on static metric threshold, machine learning-driven systems adapt in near real time to changing environments, detecting unknown anomalies, and provide actionable insights.
Thank you for that answer, Panos. My next question would be regarding LLMs. And these large language models are increasingly used in root cause analysis. Can you share an example of how LLMs have helped pinpoint issues when it comes to such complex systems?
Sure. I'm going to give a very real example as well. The game changer for large language models is their ability to understand unstructured data, right? Identify patterns in them and generate human readable explanations. That makes them uniquely suited for this task for root cause analysis. A typical scenario might involve, debugging an outage in a complex distributed system. For our scope, for example, for what we do in retail, imagine an e-commerce platform that uses a microservices architecture, right? During a high traffic event, for example, Black Friday or similar, customers report intermittent failures while trying to complete transactions, right? This pretty much means dollars on the line, like we are actually losing, the business is losing money. The system comprises of dozens of microservices, including services for user authentication, inventory management, payment processing, order fulfillment. All those have their own telemetry signals like clock, metrics, and tracing. They're being generated at massive scale across them. We're talking about probably terabytes of data. And manual debugging in this context is a daunting task, right? So the traditional challenge for root cause analysis within this context is that, first of all, logs are too voluminous, really. Like there's just a lot of them, right? They are faced with the task of sifting through that data with no other tooling except a querying language and an observability backend, pretty much. It's like, looking for a needle in a haystack, pretty much. Unless you have existing alerts based on patterns that you have encountered in the past. But if it's a novel problem, you don't really know what you're looking for. Distributed dependencies, right? So failures could result from cascading issues across downstream or upstream in a given service, making it difficult to pinpoint exactly where the problem is. And finally, time pressure, right? If it happens during such an important shopping event, for example, customers are impacted. There is pressure around resolving the issue quickly, and it leaves very little room for any sort of trial and error approach, right? You need to know what you're doing and you need to do it fast. So given this context, LLMs help in 4 ways. The first step is parsing and summarizing logs, right? Those logs are usually unstructured. They are very verbose, and they often contain redundant information or completely irrelevant to the incident details. The LLM can be fine-tuned to process logs from multiple services based on engineer prompting the system. Analyzing distributed traces, pretty much the same thing as for logs, but for traces, correlating all those signals together, especially if you're using a data framework like OpenTelemetry, and finally generating hypotheses, right? For root cause, as in you need actionable insights, the hypothesis about what the root cause is to be able to guide the efforts of the responder. Yeah.
Thank you for that insightful answer, Panos. I'm curious to hear about some challenges or hurdles that you've come across in your experience. And also many organizations struggle when it comes to adopting machine learning driven observability. In your experience, what are some common barriers, and how can teams and organizations overcome them?
I don't think this is unique to observability, but you're right. There are significant organizational usually hurdles around adoption. Of course, the potential for more intelligent, proactive, and scalable monitoring is compelling, but the more important barriers probably are data quality. And I think, again, this extends beyond observability. Lack of trust in the foundational models. And worst of all, in my opinion, is the skill gap, right? Even if you have access to the latest and greatest large language models, even if your data is great, and more often than not, they're not, having the skills to build and more importantly, improve LLM-based systems is the most major hurdle in the industry right now. We have come to a point where being a software engineer without know-how of at least how LLM systems work is counterproductive to your original mission statement. So I think that organizations need to address these issues strategically, upskill their existing workforce accordingly, to unlock the full potential, the full promise of machine learning systems in production.
And to sum up today's talk, I would like to ask you, what is your vision when it comes to observability? Where do you see this industry heading in the next, let's say, 3 to 5 years? And what role will AI play in shaping its future?
I'll start by saying that in the past 5 years, the observability landscape has undergone a profound transformation, driven by the increasing complexity of modern systems. For example, the transition from virtual machine-based workloads to containerized workloads, to cloud-native systems based on Kubernetes. So that explosion of data and the growing reliance on cloud providers is pretty much the story that we are currently dealing with. We just have to observe a lot more data. Over the next 3 to 5 years, exactly because of how expensive it has become due to the growth of data, what I think is going to happen is that observability is going to evolve from a reactive infrastructure-focused discipline into a proactive, autonomous, and business-aligned practice, with AI being at the center of this transformation. It will enable smarter, faster, and more scalable systems overall. The ultimate goal here will be to empower organizations to deliver highly reliable, performant, and user-centric systems in an increasingly complex and dynamic business world.
Thank you, Panos, once again, and I'm sure that all attendees who will attend your session and who work in engineering will find your insights valuable. And also thank you for today's talk. And I highly invite everyone who's listening to this discussion to attend Panos' session at the summit. And Panos, thank you very much for your time, and I hope to see you at the summit and hear more from you.
Thanks for the time, for the opportunity, Jana. I'll see you in Stockholm.